In the year 1054, farmers in China looked up and saw a new star burning in daylight. It stayed visible for 23 days without setting, bright enough to read by, bright enough to frighten. Then it faded, dimmed into the night sky, and within 2 years it was gone. What those farmers didn't know was that they hadn't watched a star being born. They had watched one die. And nearly 1,000 years later, that same explosion is still going. It never stopped. NASA's Hubble Space Telescope just pointed its camera at the wreckage again, 25 years after its first close look, and found something that shouldn't be possible for an event that old motion. Real, measurable, still happening motion. The explosion that lit up medieval skies has not finished exploding. That object is the Crab Nebula, and what Hubble has just confirmed is that it is not a static leftover, a cooling scar frozen in place. It is a living wound, still tearing itself further apart, 6,500 light-years from Earth. The new observations come from a team using Hubble's Wide Field Camera 3, comparing fresh images against ones the telescope captured a quarter-century earlier. Astronomer William Blair, who has spent decades studying this object, said the level of detail visible now still caught him off guard. The filaments of gas inside the nebula aren't just glowing. They're moving, twisting, colliding, reshaping themselves in front of our eyes, on a timescale short enough for a single human career to witness the difference. A paper describing the findings has been published in the Astrophysical Journal, and it does something almost nobody expected from a supernova recorded during the reign of a Song dynasty emperor. It turns a 1,000-year-old event into a live broadcast. To understand why that's strange, you have to throw out what you think an explosion looks like. A firework detonates in under a second. A car crash is over before you can process it. Our instinct is that explosion means fast, violent, and finished. But a star isn't a stick of dynamite. When a massive star runs out of fuel and collapses, the shockwave that rips it apart pushes material outward at thousands of kilometers per second. And that material just keeps going, plowing into space with nothing to stop it. The blast isn't a moment, it's a process. Nothing in the vacuum of space applies the brakes, so debris that left the star in 1054 is right now still spreading outward, still crashing into gas it left behind, still glowing from the friction of that collision. The explosion looks instantaneous only because we're used to explosions that happen inside an atmosphere where air resistance kills the motion in seconds. Take the air away, and an explosion can outlive the civilization that first saw it. Scale makes this easier to picture. The Crab Nebula, as it stands today, stretches roughly 11 light-years across, which means the gas at its outer edge has already traveled a distance it would take light itself over a decade to cross. It got there by moving it somewhere around 1,500 kilometers per second, fast enough to cross the distance from New York to Los Angeles in under 3 seconds. And yet, because the nebula itself is so enormous, that blistering speed still only shifts individual filaments by a barely perceptible amount from one Hubble image to the next. It's less like watching a bomb go off and more like watching the tip of a minute hand. The motion is real, and it is fast, but the canvas is so vast that you only notice it if you check back after enough time has passed. The story of how we got here starts long before Hubble. Astronomers in China recorded the 1054 event as a guest star, carefully noting its position and how long it stayed bright, and those records survived. Court astronomers in Japan wrote down similar observations around the same time, and Arab scholars further west also left accounts of an unusually brilliant new light in the sky that year. Some researchers even point to a rock carving in what's now the American Southwest, a star drawn beside a crescent moon in a position that roughly matches where the supernova would have appeared, though that particular connection remains debated rather than confirmed. What isn't in dispute is that people across 3 continents, working with nothing but their eyes and no shared communication between them, all noticed the same thing happen in the same patch of sky. In the 1700s, telescopes powerful enough to resolve faint deep sky objects picked up a strange filamentary cloud in roughly that same location. And later observers nicknamed it the Crab Nebula because its wispy, leg-like structures reminded someone of the animal. For 2 centuries, nobody connected the dots between the medieval guest star and this smudge of gas. Then, in the mid-20th century, the astronomer Edwin Hubble, the same man the space telescope is named after, was among those who linked the nebula's expansion pattern back to the ancient Chinese sighting. Run the clock backward on how fast the gas was spreading, and you land almost exactly on the year 1054. The cloud wasn't just some old nebula, it was the crime scene, still smoking. The final piece of the puzzle didn't arrive until 1968, when radio astronomers discovered that the center of the Crab Nebula was pulsing with astonishing regularity, a discovery that came only a year after pulsars themselves had first been identified as a real astronomical object, rather than a strange signal to be explained away. The object at the crab's heart turned out to be a neutron star left behind by the original collapse, spinning fast enough to sweep its radiation past Earth like a lighthouse beam. It was one of the first solid links ever established between a known historical supernova and the collapsed corpse it leaves behind, and it turned the Crab Nebula from a pretty picture into a physics laboratory. Fast forward to the year 2000, and the newly repaired Hubble Space Telescope, the one named after Edwin Hubble, turned its optics on the Crab Nebula and produced the most detailed portrait of the object anyone had ever seen. That image became one of the telescope's signature achievements, a violent tangle of orange and red filaments wrapped around a ghostly blue core. It was stunning. It was also, astronomers knew even then, just a single frame in a much longer film. 25 years is a blink of an eye for a supernova remnant, but it's long enough for a space telescope to check whether anything has actually changed. So they went back. What they found is the reveal at the center of this story. By lining up the 2025 images against the 2000 ones, pixel by pixel, researchers could track individual filaments of gas as they crept outward, some clumps colliding with each other, some twisting into new shapes that didn't exist in the earlier photos. This isn't inference from theory. It's direct, visual, side-by-side proof that a supernova remnant from 1,000 years ago is still actively expanding, still actively evolving, close enough to Earth and bright enough to photograph the difference within a single human lifetime. Hubble's 2009 servicing mission, the last time astronauts physically upgraded its instruments, installed the Wide Field Camera 3 that made this comparison sharp enough to trust. Without that leap in resolution, the motion might have stayed buried in the noise. Here's where the story pulls back to breathe for a second, because it's worth sitting with what's actually being claimed. A star that a farmer in the 11th century could have watched with nothing but his own eyes is still, today, detonating outward in front of a telescope orbiting Earth. The explosion is nearly 1,000 years old. It is not over. And we now have photographic proof taken 25 years apart that shows it happening in real time. So what's actually powering all of this motion this long after the original blast? A supernova explosion is violent, but violence alone doesn't explain a wound that's still active 1,000 years later. The answer is that neutron star at the center, the Crab pulsar, spinning roughly 30 times every second. A dense, collapsed object that's small, spinning that fast, doesn't just sit there quietly. It flings out a continuous wind of charged particles and energy, and that wind slams into the surrounding gas from the inside, like a fan constantly blowing into a slowly expanding balloon. That ongoing push is why the filaments are still colliding and reshaping instead of just coasting outward and cooling down the way a normal explosion would. The blast that happened in 1054 supplied the initial shove. The pulsar has been supplying fresh energy ever since, for nearly 1,000 years, and shows no sign of stopping anytime soon. The explosion isn't coasting on momentum alone. It's being fed. That distinction matters because it changes what kind of event we're actually watching. Most supernovae fade fast. In 2018, Hubble caught a different exploding star, cataloged SN 2018 GV, in a galaxy called NGC 2525, 70 million light-years away, and turned a year of observations into a time-lapse. The star flares up bright enough to rival the core of its host galaxy, then, over the following months, fades back into obscurity, gone within a year. That's the ordinary lifespan of a visible supernova. Bright, brief, over. The Crab Nebula is the opposite case. It's what happens when the dead star at the center refuses to go quiet, when the corpse itself becomes the thing that keeps the explosion alive. Most stellar deaths end. This one is still, in a sense, happening. If you're keeping track of where this story sits between confirmed and uncertain, here's the honest shape of it. What's firmly established, the 2000 and 2025 Hubble images show measurable outward motion in the nebulas. Filaments? The comparison has been published and reviewed, and the Crab pulsar's existence and spin rate are well documented from decades of independent observation. What's still being refined? The exact three-dimensional structure of the filaments, since we're viewing a tangled, layered object in only 2 dimensions from one fixed angle, and the precise reasons some filaments appear to move faster or collide more violently than others. Astronomers can measure the motion with confidence. Modeling exactly why every individual strand behaves the way it does is a harder, ongoing puzzle. That's not a weakness in the finding. It's the normal state of a live investigation into an object that keeps giving researchers new data every time they check back in, rather than a solved case filed away and forgotten. The bigger reason this matters goes beyond one pretty nebula. Every supernova, including the one that lit up the sky over China in 1054, is a forge. The core collapse and the shockwave that follows don't just destroy a star, they cook new elements out of the wreckage: oxygen, carbon, iron, the raw material that eventually ends up in planets, oceans, and living things. Every atom of calcium in your bones and iron in your blood was made inside a star that eventually died in an explosion, not unlike this one. Hubble's spectroscopic observations of the Crab Nebula let scientists read the chemical fingerprint of exactly what got made and flung outward in that ancient blast. Watching the debris field continue to spread, filament by filament over 25 years, gives researchers a live laboratory for understanding how that material actually distributes itself through space, how fast, how unevenly, and what shape it takes on its way out into the galaxy. It's one thing to calculate this from theory, it's another to watch it unfold in your own set of before and after photographs. There's a practical payoff here too, beyond pure curiosity. Supernovae, like the one that created the Crab Nebula, are used as cosmic yardsticks, helping astronomers calibrate distances across the universe and refine how fast everything is expanding. A remnant this close, this well documented, and now this precisely trackable in its motion gives researchers a rare calibration point they can return to again and again, testing their models of shockwave physics and pulsar wind behavior against real, repeatable measurements instead of simulations alone. Every 25 years, the Crab Nebula effectively hands scientists a fresh dataset for free, just by sitting there and continuing to explode. There's also a quieter implication buried in this discovery, one about time itself. We tend to think of astronomy as a snapshot science, one picture of a frozen universe. The Crab Nebula breaks that assumption. It's proof that some of the most violent events in the cosmos don't happen and finish. They happen and continue, slowly enough for a single research career to catch the difference. Fast enough that it isn't just theoretical. Astronomers can now, in principle, keep returning to this same patch of sky every couple of decades and watch the story keep writing itself. The Crab Nebula isn't a historical record anymore, it's an ongoing one. Which brings the story back to where it started in 1054, with observers on 3 continents looking up at a light in the sky that had no business being there. They didn't have telescopes powerful enough to know what they were witnessing, and they had no way of knowing that they'd never actually see the end of it, because there wasn't going to be one. Not on any time scale a human life could measure. They just knew something extraordinary had appeared, blazed for weeks, and eventually faded from view. What Hubble has now shown is that the fading was never really finished. The star's outer layers are still out there, still moving, still colliding with themselves, still being driven outward by the collapsed heart of the star that used to hold them together. An event that predates most of the buildings still standing on Earth today is, this year, continuing to unfold in a set of images taken 25 years apart, and it will still be unfolding filament by filament, long after this video is uploaded. If you had access to a telescope that could revisit the same explosion every quarter century for the next 1,000 years and watch it keep changing, what part of the universe would you want to check in on first? Drop your answer, and if this kind of slow motion cosmic violence is your thing, there's another Hubble story I just like it waiting for you next.